Hello. Hi. This is me. That's the screen. I made a conscious choice not to overdo the source code for this one. There is some source code, but I have a gut feeling of a lot of source code would probably be bad. And I'm really grateful for past me. Past me made a good choice. Because current me, yeah. So, cool. Let's get this started. So this talk is, so you want to build your own programming language. A cautionary tale is the subtitle. That's not true. My name is Steve. That is some amount of my Twitter handle if you want to follow me on Twitter. It's the only reason I do these things is basically for Twitter followers. I work at a company that today is called SendGrid. See, some of you were at the last talk I did, and I feel weird reusing the jokes, but some of you weren't, and you deserve the bad jokes, right? So there was an announcement on Monday, thank you, thanks for the assist, Mark, that Twilio was going to acquire SendGrid, at which point legal got a statement approved by the SEC of what I'm allowed to say about that. I did not read that statement, so I will say nothing about it. But if you were ever interested in working either A, SendGrid, or B, Twilio in 90 days, that is bit.ly/sg-fee. We're hiring a front-end engineer 2 role, which I like to explain is usually a great second job for an engineer. So around 2 to 5 years of experience, because that's not at all too wide of a range. Because an engineer with 2 years experience is exactly the same as an engineer with 5. I don't read those personally. I applied for a role that was, my current role is 9 to 12 years of experience, because that's a thing in JavaScript. So I don't take those seriously. So if you're interested, apply, go for it. I believe in you. So we're going to talk about building your own programming language. And if there's a little piece of you that is slightly suspicious that one could talk about building a programming language in 30 to 45 minutes, you're probably right. This is going to be kind of the 10,000-foot view of the lay of the land of building a programming language, right? And I think it's really useful because I think there are a lot of concepts in here that you could, there are things we don't write our own programming language at SendGrid. I know, I think it's Node-RED Inc. has Elm. Facebook's got 45 languages that they've written. Reason, JSX if you count that, so on and so forth. But we use various pieces from this buffet of tools and technologies to actually solve real-world problems. So what I wanted to do was kind of give you the high-level overview. If this is something that's super interesting to you, this talk is the result of taking effectively 6 hours of content and cutting slides mercilessly until it wasn't totally embarrassing to stand up here in front of you. So my plan is to do kind of a longer form version of this, a 6-hour version of it, in December. I'm going to actually do a recorded version for front-end masters at one point, but I kind of wanted to do it in front of a live studio audience first. So I'm going to do a version of that probably early December, late November. If you're interested in actually getting in the weeds and writing a bunch of code and building your own abstractions and stuff around this, that is totally a thing that we'll do, and I will totally email you about this. Now, let's just get the obvious thing out of the way. TinyLetter is powered by MailChimp. I don't want to talk about it. SendGrid doesn't have sign-up forms. We're working on it. Next quarter, I will totally move everything over. Yes, I understand. So is the Dinosaur.js mailing list. It's all MailChimp. I get it. It's not at all embarrassing. Cool. Glad we're recording that. Moving on. So the kind of good news is, I think it seems really intimidating, right? And in 25 minutes, again, we're going to do the high-level 10,000-foot view. But as long as you rein in your ambitions, I think, what is it, George W. Bush just said, the soft bigotry of low expectations? As long as you rein in your ambitions, building a programming language is actually suspiciously easy. And what do I mean by that? Well, I mean basically that if you want to get into like advanced like memory management on a CPU level, very hard, right? If, on the other hand, you're like, I want to extend to JavaScript, yeah, you can do that. If I want to have a compiled JavaScript language, yeah, you can do that. If I want to like have something like Sass or Less or handlebars that I want to build, yeah, that's well within probably your existing skill set. And so that's kind of the major message that I want to kind of get across today is like, yes, those things are way easier than you expect. If your plan is to write the next Swift, like most of that level stuff is handled by PhDs. And like, not to say you couldn't do it, but like that is definitely a heavier lift. But for the kind of like most practical use cases that most of us want to do, not on a dedicated team, it's like the V8 compiler in Chrome is not written by some engineers in their free time, right? But a lot of stuff like Babel was, right? Sebastian was, I think, like 17 or 18 when he wrote Babel, right? That, by definition, means not a computer science degree, right? I think a lot of this stuff is very accessible and doable once you kind of like get the high-level concepts. And that's my job today, is to convince you that you can totally do this, right? We should probably cover like why you would ever want to do this. Like I said a second or two ago, we're going to talk about the whole lay of the land, and you might want to do the whole, like from syntax all the way to a compilation target that is JavaScript or something along those lines, or even actual like machine code. But one thing I want to like keep your ears open for is given pieces of this are also usable in isolation, right? And so for me, this talk came out of, we had a bunch of like very like real problems to solve in our production application, and pieces of this solve those problems for us, right? In just day-to-day, oh, we have to do this thing. And Mark will argue with you that I have over-engineered everything, and that's probably fair, but that's my job, so whatever. So yeah, all of this is usable in given pieces, and sometimes I will say like, hey, this is how it would work if you want to write from scratch, but also there might be a library that does this piece for you, because if there's not that piece that you need, you can kind of mix and match your own custom implementation with third-party libraries. A lot of them are like built into Babel. Like you normally think about Babel, yeah, I set up in Webpack and I get stuff coming out the other end, but like there's libraries inside of Babel that you can use for doing pieces and parts of this. And we use a lot of that. Like in some cases, we'll use an off-the-shelf HTML parser, right? And then we'll do stuff with the tree that we get from that. But like there are definitely like little pieces that you can use day to day. Have I beaten that horse to death sufficiently? All right, everyone's nodding, so that probably means please move on. All right, so some use cases that are the smaller ones is like a domain-specific language, like a gem file. Like if you do Node, package.json is a JSON file, fine, but that actually has a parser. It needs to get like evaluated. Gem files are slightly different. Terraform for creating cloud deployments, right? There, like Sass is effectively a really great like version of this, right? Same thing with like templating languages, which is definitely like a use case that we have at SendGrid when we have like email templates. So handlebars, Jade, or Pug, if you've ever actually hopped on the train on that one. Jade got renamed Pug for legal reasons, like honestly, what, 3-4 years ago, and nobody has ever like fully, like we all go, yeah, it's totally called Pug, Jade. And so this is a big thing that we're doing right now, or maybe you just want to do it as a hobby. That's super cool too. So there's practical reasons, there's impractical reasons. I think both are very, very valid. And apparently I really felt strongly about making this point a lot of times. That's why there's like 6 slides. So here we are again. You can use pieces of this. Very cool. So how do we use it at SendGrid? So we have a drag and drop editor. So SendGrid is predominantly known for their email API that every time you take an Uber or lose a eBay bid when you've been drinking too much, we send you that email, because sending one email is easy, sending a billion emails is difficult. So we have an API. I don't work on that. But it makes like 80% of the money, so I'm very happy it exists. But I work on a drag and drop editor for making emails so that an average non-developer can make pretty emails. And to do that, we take HTML, either from one of our templates, from an existing campaign that the person's making, and we parse it into like a data structure that they then manipulate in a React application. And then once they've done all the tweaking and fidgeting and dragging and dropping and moving and typing and stuff like that, we take the data structure and we like sew it back into an HTML document so we can send it to clients. So we use a lot of that in the editor. We are working on a rich templating language for taking all sorts of data that we have on users and creating very like dynamic and customizable templates. So like, okay, we have like the last like 7 orders that this person did. We can actually show those in the emails and write an entire templating language around that. Right now, that is based on handlebars, but product wants to have like a much more like rich syntax that handlebars doesn't offer. So we have to basically either A, extend handlebars, which we use some of these tools for, or B, move to creating our own templating language in the next few months as well. Like we have all the underlying code for that now, and we use a lot of the concepts that inspired this talk to do that. And then we have a side-by-side editor where you write HTML and you see the preview on the other side, and then somebody had a great idea that you should be able to click on one side and have it highlight on the other side, which we had to, again, parse and evaluate the HTML, annotate all the nodes in the DOM, figure out an event listener from when they click on it, go and highlight the code, so on and so forth. Again, none of those are necessarily like full-fledged programming languages, but they're all from the same concepts that are used in programming languages, right? They're all just basically ideas stolen from creating languages and used in tiny bits and pieces. So, if you want to build your own programming language, we're going to get you like the 10,000 foot view. We're also going to try to give you a new set of tools for solving very common problems that could be lingering in your production applications that you would probably just try to throw a ton of regex at until it hopefully worked. So basically this is a talk alternatively titled, So My QEs Don't Kill Me. Cool. Yep, another slide about that. I'm going to talk about JavaScript because I am a front-end engineer. But most of the like philosophical high-level stuff, like originally CoffeeScript was written in Ruby, right? Sass was originally written in Ruby. These are language agnostic concepts. I'm going to tie them into JavaScript because that's what I know, and like I don't need to go full charlatan on you. But let's look at some, kind of like practical examples. Like, one of the most famous is CoffeeScript. There was a book that I don't think you can buy anymore, as like how to build your own awesome programming language, and it was targeted for Ruby developers. And Jeremy Askinas read that book, and that was kind of the inspiration for CoffeeScript, right? And CoffeeScript compiled at that point. It was written in Ruby. These days, CoffeeScript is actually written in CoffeeScript. Let that wash over you for a second. We'll get to the term for that later. But modern CoffeeScript is written in CoffeeScript, but originally it was written in Ruby. The most famous thing, we had this long fight at SendGrid where a team wanted to use Elm, and the architecture team found out that like Elm was a compiled to JavaScript language, and they were like, oh, we don't want that. And I had to be the person to tell them that JavaScript is a compiled to JavaScript language. And most of the JavaScript that we write is also compiled to JavaScript. So like one of the most famous examples is JSX is not actually real, as if you ever pasted it into the console you found out. Even like a lot of the features we use like are stage 0, right? So Babel is better JavaScript to JavaScript that will work in like Safari. I didn't want to pick on IE anymore, so I'm going to pick on Safari. It's fun. It's the new cool thing. The hip kids are doing it. ESLint is another great example. You don't think about ESLint as a language that compiles to another language, but ESLint has to kind of pull apart your code and analyze it and figure out all the stuff that's going on in your code. Same idea. It's like it doesn't necessarily generate new code. It generates like obnoxious warnings and breaks the build process. It doesn't let you merge to master, but it doesn't necessarily like make a new language. But it's still the same concepts of pulling apart your code and analyzing it. Anyone know what this one is? It's Prettier. Yeah. I learned that was the logo for Prettier too today. So Prettier is a tool that basically tries to stop meaningless arguments in code review by like formatting your code for you on every save so that you don't nitpick each other about whether or not there should be a semicolon at the end of the line. right? Again, we don't think about it as a program, like a compile target, but again, it is still pulling apart the code, analyzing the data structure, adding white space, and making a whole bunch of decisions that I don't agree with, and changing all my single quotes to double quotes, because I'm a monster. But it's again the same concepts. And this one, if you've never seen it before, it doesn't have a logo. It's just written in monospace font, so I did that too. It's a tool by Facebook called JS Code Shift. And JS Code Shift is basically a way to do large refactorings in your code base. And so let's say you thought it was super important to change all the vars to const and let, right? You could do a giant find and replace and get every variable that started the word var in it also, and change that to let as well, and all that kind of stuff. But also they're different, right? You could actually break your code. So JS Code Shift is a tool for making large-scale refactorings of your code base. So when you change all the vars to let in JS Code Shift, what it does is it actually analyzes the code and figures out, okay, is this being used like a variable? Should we keep it as a variable? Is it never getting remodified? Make it a const. It actually understands the code more than just finding and replacing would, which is super cool. Usually when new versions of React come out, the Facebook team also releases code mods powered by JS Code Shift that will change a lot of your syntax to whatever the new version that you need to use is. So that's super cool. I don't know if it directly came out of this project, but one of my friends worked at Facebook at the time, and he had a tool called Recast, which is similar to Babel today. And he was working in the Facebook office in Silicon Valley, and he wanted to transfer to New York. And so while that whole transfer was happening, they kind of put him on a BS project, where his job was to change all of the ES5 classes, right, function with function prototype, so on and so forth, to ES6 classes. And so he basically wrote a version of this tool at Facebook back then, this would have been 2013, 2014, that basically went through all of Facebook's code base and rewrote the code programmatically to use ES6 classes. Right, and so there are really powerful things you can do, giant refactorings. If there's somebody who used a variable that you don't really like, you can go and find them all and rename them, or shift around the code to update to the latest thing, or find all the console logs and replace them with something that doesn't log in production, or something along those lines. There's once you start thinking about these tools, this is my hope is this is one of those talks that you're okay, cool, and then 2 weeks from now you're walking down the street and you get an idea of how you can use a piece of this to do something really cool at work. All right, what is a compiler? I have 2 slides that have way too many words on them. Are you ready for the first one? Yeah! Cool. I'm going to read it off my screen. The evaluator, which determines the meaning and expressions of the programming language, is just another program. So the TLDR here is that all a compiler is, it's just a regular, there's nothing that makes a compiler special. It's just a program that you can write that takes a giant string of text and does stuff to it, right? That's not really different than what we all do for a living. This is not you need to live in an ivory tower to do this. This is simply take words, rearrange them. You've written a compiler. And these are important because most of us do not write CPU instructions by hand. Most of us do not write assembly. Source code is meant to be human readable, unless it's Perl. Case in point, this is the brainfuck programming language. That is the real name of the programming language. See? Human readable. Am I right? This is this console logs hello world, if you were wondering. Cool. So when we're building a compiler, there are 3 major stages. And again, this is again, I asked you if we were done beating the dead horse. I clearly ignored your answer. Which is any of these can be used in isolation. So really the 3 stages of a compiler is parsing, where we take the source code and turn it into an actual data structure that we can work with. In a second I'm going to make believe this is really 2 stages, so I'm not a hypocrite, I just, this is the real thing, and then I'll tell you my fake version in a second. Once we have a data structure we know how to work with, then we need to transform it from whatever the kind of source language was to whatever the compilation target is, right? That could be machine code, it could be assembly, it could be JavaScript, it could be CSS, right? It could be anything along those lines. right? So once we have a data structure we know how to use, we take it and we transform it into like another data structure that can then be turned back into whatever our compilation target was. Again, CSS, JavaScript, machine code, JVM bytecode, what have you, right? So we take it, we pull it apart, we rearrange it, and we put it back together again. That's all it is. It's just like taking anything out of a database, doing stuff with it, and making an HTML page. It's not that much different. So let's start with parsing, shall we? Like I said, I'm going to pull parsing into two major pieces. I'm going to make it lexical analysis and syntactic analysis. Not joke of psychoanalysis. Cool. So we're going to call, because I don't want to say lexical analysis that many times, we're going to call it Lexing. We're going to call the program that does it a Lexer, because that is way easier to say. Basically, the job is you take that file off the file system, you read the file, it is a big string of text with some new lines in it. Your job is to like break it up into little pieces, right? Like it's a giant like, if those two letters might mean something, right? So on and so forth, right? Go ahead and figure out all the little pieces in there and chunk them up, and so you know what they are and relatively. You don't necessarily know how they all interact together yet, but like break it up into the component pieces. So we call it tokenizing in a lot of cases, where again, we take the giant string, we break it up into tokens. How might a Lexer work? We accept an input string of code, either we read it off the file system or wherever you get it from. We create like a variable for figuring out where we are, like the index, if you will. I'm going to call it a cursor today, but like the index of where you are in that string. Then we'll make an empty array for all of our tokens, and then we'll iterate through that string, and as we figure out things that we know what they mean, we'll kind of take them and we'll create little objects that we put in the array. We'll see if it matches one of our known types, and we add it in. Cool. So you could, I think a very simple way to do this with a little bit of regex, like again, don't get carried away with regex, but like we can definitely use it for figuring out like what a white space character is, what a number is. In this case I'm just doing like a simple calculator. What a given plus, minus, divide or multiplication symbol is, right? All of these functions here will tell me, oh, is this next character I'm coming across one of these things, right? Then we know what kind of token to turn it into as we go along. So we could have a function called tokenize that takes this input. We start the cursor at 0. We start with an empty array of tokens. Until we get to the end of the string, we start moving through the string. So for instance, to figure out if it's a plus, a minus, a multiplication, or division operator, right? We'll use that is operator that just checks to see if it's one of those. It doesn't have to be regex. Like when I wrote our current, our custom handlebars is called whiskers. Get it? I didn't come up with that one. I wanted Fu Manchu. The other team named it first. I lost. It's fine. I'm not bitter. I'm not spending way too long talking about it right now. Take a sip of this beer. And so our syntax of we cheat right now, which is like we basically turn whiskers into handlebars and then we run it through the handlebars compiler. A little bit computationally expensive, but also really easy to implement. So cool, if it is an operator, we create a token. This is JavaScript, so I'm just making a plain old JavaScript object. I'm going to say it's the type of operator. I'm going to say the value is the plus, the subtraction symbol, the multiplication symbol, the division symbol. And then we increment the cursor and we keep going, right? This is happening in that while loop. We're just going through each thing, we're just identifying each character. A number, this is not going to work. It might be the same thing, like check to see if it's a number. If so, make it a token of the type number, and whatever the value was, move along. White space, we actually don't care about white space in my little calculator language, right? Like if you're writing Python, if you're making a Python clone where like white space is meaningful, you would need to keep track of white space, right? Because that's like blocks in Python. But in my little language right now, actually white space is not meaningful. It just means that we're not in the current same token anymore, right? Like there's some space in there, but I don't need to keep track of that. Things like ESLint might, if they're just trying to like shuffle your code around, but in this case, I don't need to make a token for it, it's just white space moving along. So if I had this expression 2 plus 3, these are the tokens that I would end up with. I'd end up with number, right? A number token with the value of 2, an operator token with the value of plus, a number token with a value of 3, and this would be my entire program at this point, right? Like you might not necessarily keep track of semicolons, but you might say like, okay, this is the end of an expression. so on and so forth. This code that I just showed you has a problem, which is it works great for single-digit numbers, right? If I give it 22 plus 23, I'm not going to get a token with the value of 22 and a token with the value of 23 just yet. I'm going to get too many tokens that I don't know how to deal with just yet. So over time, you can add some extra logic to start to solve this. We can say like, hey, if I come across a number token, right, assume that I'm building up this number until the point where I like come across something that is not another number token. Right, so here in the first line, we say like, all right, it's a number, we're doing numbers. Very cool. We'll keep some kind of variable to just hold on to that. We'll start with the first digit that we came across. And we'll say like, while we keep coming across numbers, concatenate them onto that first number. So 22, like if we came across a number, it might be 225, so on and so forth. Keep building up this current number, and eventually, when you no longer come across numbers, then we will go ahead and push that token on. So now I'll actually get something that makes a little bit more sense. So here we'll be able to do 22 plus 23, right? Now, clearly there are more than just mathematical operations in a programming language. We might need to deal with ifs. You might have a whole bunch of keywords or identifiers that you come across. You would also do a very similar concept for each of those. My sense is that going through every single thing you can find in a language that you write now and showing you roughly the same code will bore the living poop out of you. So I won't do that, but we'll start with the same basic concepts, right? So we've gone through the string of code, we hit the end of it, we've created all the tokens, we've figured out all the chunks of our language, right? We figured out where we found an if, where we found an open parenthesis, where we found a bracket, so on and so forth. We've identified all the pieces of it, we've ignored what we don't care about, we've kept track of what we do care about, and we're ready to figure out like what it all means. Because like just simply going, yep, number, string, parenthesis, like that's cool, like you need to do it, but like that does not a programming language make. So the second part of parsing is once we've identified all the pieces, figuring out their relationship to each other, figuring out what they all mean and how they all work together. So eventually, what we call it in a lot of cases is some internal representation of the language. In most cases, this will be what we call an abstract syntax tree. An abstract syntax tree is basically like a tree-like structure that shows like your program. We're going to look at some diagrams of ASTs in a second. We do a lot of work with them at SendGrid for a lot of stuff that we do. I think they're really cool. Cool. So we broke into tokens, figure out how to arrange them. Now we know the meaning of the program. We know that like that return was inside of a function. Okay, that means something different than if it was somewhere else, right? So it's all incredibly important and useful. Let's go ahead and take a look at. I regret this decision. All right, we're better. I'm back. Got two hands now. Let's go ahead and we'll take a look at a really useful tool that I use a lot, which is called AST Explorer. All right, this is gonna be fun. So here we have one. Let's boost up that font just a little bit. So I have some JavaScript in here. It is add x and what? That's not even valid. Real time. Hey, now it is. So this is a simple function in JavaScript that is adding a plus b, and over here you can see this is the tree-like structure. Let's see if I can. All right, so we got a file. In there we have a program. And you can see like it starts on 0, it ends on character 38, so on and so forth. Okay, there's a function declaration. There's an identifier. You can see the yellow. That's like the add. If I go in there and look at it. You can see it's an identifier. Its name is add. It's all of the different like pieces of the code arranged. In there, it's got a set of parameters, right? A and B. After that, there's a block statement. It's the shape of our programming language. This tool is really cool because like this is JavaScript with Babel, but you can see that like it can like show you ASTs for CSS, for handlebars, for HTML, for Lua maybe, Markdown. I think that looks like PHP. Like it'll show you the ASTs for all of these, and for each language, there's a bunch of different parsers. So if you know you're using one of these tools and you want to see the AST that would get built for you, you can see it in this really awesome tool. And it'll give you, like again, either one that you click on, it'll show you it in the other side of it. So if you go here, you'll get the return. You can kind of see the tree-like data structure without lines in the middle. It's better. All right, back to the slides. So here is for a very simple program of x equals 2. It's again, this is the tree-like structure. There's not a lot of pieces in here. We have a variable declaration of x, the declarator, to kind of like, the equal sign is the declarator in this case, right? It's like, it does equals in terms of equality, it's an assignment. And then you have what is on the left and what is on the right. Again, I'm using code that I know I can fit on slides here. Like you saw a much larger, an add function was larger, right? But you can actually paste a full program in there and explore the tree. And you saw that it had like line numbers and stuff like that. That's useful for stuff like ESLint. This is console log, where you can see an expression, right? That's everything from the C to the semicolon. And there's a call expression, which is a function call. You can see the member expression is the console object and then the log method on there. And then you can see in that tree the argument is hello. So now you have this you have a data structure. If you needed to change this, like let's say you were writing Babel with this, you would be able to take this tree and it's like, oh, here's a thing that's not supported in like IE 5.5. You can simply work through the tree and start moving stuff around and rearranging it, and then you can spit out new and different code. Right? This is using Babel's parser, but theoretically we saw how to write a Lexer. You can create your own trees, and if you can just modify that tree into something that the Babel compiler understands, you can spit out JavaScript. You can use very small pieces of this as you need it. Oh, JavaScript's my compilation target. As long as you can make a tree that the Babel generator understands, you can compile to JavaScript, right? Right out of the box, or using some of these pieces along the way. So this is our A and B function from earlier, showing you just again the same tree visually. One of the really cool things, if you are targeting JavaScript, is you saw that there was a whole long list of different parsers out there. Dave Herman, who also did a lot of work on Rust in Mozilla, made kind of a tree structure, Mozilla being open source and stuff along those lines. All of the other implementations, Esprima, Acorn, which is the basis of Babel, so on and so forth, they all kind of converge on this ES tree spec. So a lot of the parsers all generate, most things that compile from JavaScript to JavaScript use the same AST standard in air quotes along the way, which means that if you can generate to this kind of spec compliant tree, then you are able to kind of compile to JavaScript as a target really easily. It's also, if you don't have strong opinions on what your tree should look like, you should probably just look at this, right? Because at least there's inspiration. Maybe you're writing a brand new language from scratch. It's not going to just be like JavaScript, but you know if you wanted to hit that compilation target, what you'd have to turn that tree into. It's a really great, well-documented implementation of this that you should definitely check out. So how would you build an AST? I'm going to show you a link towards the end of this. One of my friends, James Kyle, who worked on Babel, has this thing called the super tiny compiler. It basically takes a Lisp-like language and turns it into a Babel syntax tree, but he annotated the code really well, so you can see each step. It's the thing that makes the AST is 200 lines of code with copious comments. It's probably only 30 or 40 lines of code, which is a whole description of everything going along the way. I'm not going to read that to you right now, but I will have a link to it at the end. So we're going to use pieces of that here with permission. And so, cool, we have our array of tokens. We iterate through that array of tokens now that we have it. And for each number, string, function keyword, if statement, we add that to the same level of the tree, right? So if you see a number, that's going to be just appear to something else. In James's version, it's a Lisp language, so there's function calls, and at which point you then recurse in, right? And that gives each new layer of the tree. So, okay, we handle a function call, those are going to be parameters, recurse down, it'll be the next layer of the tree, recurse on up again. So he's got this function, which has got a parser. Again, we have this cursor variable again, and he's got a walk function. And the walk function goes through whatever token we're currently on. And if it comes across a number, it iterates to the next token, and it returns this number literal AST, or abstract syntax tree leaf, or node, right, with that value on it. The same thing for like strings, or anything along those lines. It's only interesting when it comes across, in a Lisp-like language, a parentheses, because that means a function call, right? At which point, like, oh, we've entered into parentheses, now go recurse into that one and figure out what that all means, and just add that entire expression onto the tree, just like we saw before with the console log. And so same basic idea, it'll use that walk function again, it'll do the same thing and create each node of the tree. I definitely recommend checking this out. So we're talking in terms of programming languages. Again, we use it for pulling apart HTML and modifying that HTML before we sew it back together again. That's what we use in our design editor. We use it for keeping the two sides of our editor in sync. We use it for, Handlebars uses it for creating HTML as well. There's a lot of really useful use cases here, like ESLint uses it, Prettier uses it, all these code shifts use it even if you're not building your own language. If writing all this code seems terrible to you, there is a series of tools out there. They exist in almost every language. The first one is what's called YACC, Y-A-C-C, and that is yet another compiler. And then it had Bison, and then there is one in JavaScript called JSON, which I'll show you in a second. But basically there are a bunch of tools that will actually, they have these grammars that are language agnostic, and then they will generate lexers and parsers for you in your given language. And I'm going to show you a way too long quote. Everyone cool with that? It's basically one of the creators of C++, who also created the D language, basically saying they are a waste of time because when you see them, they are their own language, right? So now instead of writing JavaScript to parse and lex, you are writing JSON, or Nearly, or a Bacchus Noor form, or something along those lines, and then you're tied to that. I'm of two minds about it. Like, I think it is, like, depending on how complicated your language can get, it can be tricky, and a lot of these will solve a lot of the problems for you. But there's a certain truth to this quote, where, like, yeah, then you are tied to that tool unless you want to rewrite it. So, like, make the choice. It's cool. One of them is called PEG.js, which is Parser Expression Generator. And there's no way we're going to see this one, but this is a simple math one. It's basically, you describe all the rules of the grammar. You describe what's an operator, what's a number, stuff along those lines. I've got a slightly larger one in a second coming up. And it basically produces a program that will parse and lex your thing. So it comes with a bunch, like a lot of, I think Ruby has a parser generator kind of used for a really long time. CoffeeScript had one. This is one that will actually parse CSS for you and give you an AST, right? It's written in JavaScript and you can just use it. So there's some advantage to these, right? So you can see this is a rule, this is, it's not important. You get all the information about it, and you could theoretically manipulate the JavaScript, the CSS in this case, and be able to see like the next thing that's happening. JSON is another one. Like, you can see, none of these look less intimidating to me than writing it by hand. So I would recommend play around with it, but like, don't feel that you're not like legit if you use one or don't use one. They're all tricky. Every time I've done this, I've written my own JavaScript, but I definitely like see value. If you're especially doing something like a little bit more complicated. In the JSON, I think the interesting part, that's really convenient. Is you can see that for the caret, which is usually what we use for squared or to the power of 4, that all it's doing is saying like, oh, if you see a number, then a caret, and then another number, which is what that E is, change that to math.pow, which is JavaScript, right? So it's about taking a calculator and turning it into real JavaScript. It's saying all the rules for how you just declare all the rules. It generates a parser and lexer for you and works. You can even see the bang for factorial. down below will actually create a new function called factorial, and it'll do it. So this is about compiling like math to math, a simple calculator to JavaScript. If you're going from JavaScript to JavaScript and you just want to modify that JavaScript, Babel has one that works. It like has a bunch of plugins for like stage 0 and future JavaScript. The big problem with Babel Parser is it doesn't have a plugin architecture. So you're like, I want to add my own custom syntax to JavaScript. I'll show you how to do that in a little bit. Or I'll show you a tool to do that in a little bit. They don't have that right now. They don't have a plugin architecture. You'd have to like fork the Babel Parser. But you can basically pull in Babel Parser if you're just trying to modify your JavaScript. This will basically, the parser will create you an AST out of any string of JavaScript along the way. So now we've got this AST, we need to transform it. All transformation is we take our internal representation and we start modifying it until we get something where we can create the output that we want. So yeah, manipulate it, do your thing. Most of the time this is using this pattern called the visitor pattern, which is from that fancy design patterns book that none of us have actually read. And this is a diagram that shows you the visitor pattern. This makes sense to everyone, right?
Yes.
Sweet. Moving on. So basically all of it is you do a depth first search of that tree. That was a joke, we're not actually moving on. You do a depth first search of the tree and you kind of go through it, and the visitor pattern basically says, okay, if you come across a function call, do this. If you come across a number, do this. If you come, like, it basically gives you a thing for any given kind of token I'm on, cool, do the next thing. And like, if you're using Babel's traverse for this, which we'll see in a second, there'll be methods like, okay, I came to a plus sign. Let's say for some reason you're writing a Babel plugin that took two sides of a plus and rearranged them. Right, you can like, it gives you methods for getting to the one to the token to the right, the token to the left, and like switching them and stuff along those. It gives you all the tools to modify the tree. So the visitor pattern goes through, for each of them one we'll find it. And I'll show you in code real quick. We'll see how it works on the screen. Who's ready? I think it's gonna fit right in between those two. I think it's gonna be good. Yes! So Babel traverse has a traverse method which takes your AST, and basically visitor pattern has enter and exit. So you're entering a node, you're leaving a node, and it will pass you the path of the node and everything about it in there where you can do stuff. So here we're saying, hey, if the node type is a variable declaration and it's the kind of var, change it to let. This is not as fancy as that JS code shift one we were talking about earlier, but it's a very like simple one that I can fit in between the two bars there. And we can kind of see it go through the code. If it is a variable declaration, do this thing. Cool. And like, again, we use this a lot. We take our HTML, we turn it into an AST, we turn it back into HTML. Runtime model, we're not going to talk a little bit about. This is how you actually manage memory and types and all of those. Like, we're talking mostly about like taking fancy CSS or Sass and turning it into CSS, so on and so forth. Not so much about like actual deep memory management, but this is like a core part of like we'll call them real programming languages, like Go. Like you've got to write a garbage collector and stuff like that. We're totally cheating. We're just going to transpile to other languages in this talk, so sorry. But I do want to like talk a little bit how it works. So how does JavaScript get compiled? We download it off the internet. It gets parsed in Chrome or Safari or Firefox or whatever, and it gets turned into an AST when it gets to the browser. This is all the way that real JavaScript works, even outside of the tools that we've been talking about. At which point it just gets turned into bytecode, but actually a bunch of PhDs, like my friend Francisco works on this, and they will run your code, but that can be slow, so then they start collecting information about your code and bring it to this thing called turbofan, which then like actually does like x86 or ARM machine code once it knows enough about the code, because JavaScript's not typed, so it has to do a whole bunch of like funny like PhD level stuff that I don't really understand. I just nod while she talks, and like does all that. So this all happens in the browser with your code as well. This is not just like fake like Babel Sass stuff either. All right, last phase, generation, or as I like to call it, parsing in reverse. Before we took a string, we turned it to a tree. Then we modified the tree. Now you know what we got to do? Turn it back into code. And then let Chrome do the rest in the runtime model. There are a bunch of options. Like we're going to talk about, compiling the JavaScript or Sass or even Ruby if you wanted to. But clearly, like you can compile it to like low-level CPU instructions if that's your idea of a good time. There's also LLVM, low-level virtual machine, written predominantly by Chris Ladner, who made Swift at Apple. It's also what Rust uses. It is generally the kind of compiled target for even what we consider real languages, because it handles like a lot of that stuff for us. You could target the Java virtual machine as well, like this is what Scala does, Clojure does. Kotlin, and a few other languages like that. Or you can transpile it to like CSS or JavaScript because it's 2018. If you have a Babel compliant tree, and we saw before that's like ES tree, you can actually go ahead and just use Babel generator for this part. You don't actually have to do this yourself. If you can get it to a Babel compliant tree, you can just use an off the shelf for this last mile. Right? That's assuming that JavaScript is your target. If not, you need to find something else. And it's a really easy function. You give it the EST, you give it some options on whether or not to try to keep the new lines, and then you give it the original code so it can make source maps for you. And out the other end, you will get legit JavaScript at this point that'll just work, right? So at this point, you at least have all the tools, and you have to like write a Babel plugin if you wanted to add, some new features or like modify your code. All right, some bonus terms that I couldn't work into the talk any other way. So there's no actual like thought process as we go into this one. When you come across a word like this as you're doing the research, you can't not challenge yourself to try to say it out loud in front of a room full of people. Sip. Homoiconicity is a language that can modify its own data structure. Don't try to like correct me on the spot, Mark, on my pronunciation of this. And so these are languages that can modify themselves. Like Lisps are really good at this. Like anything that has like macros along the way. And then self-hosting is when you all looked at me when I said CoffeeScript was written in CoffeeScript. That is what we call a self-hosting language, when the language is written in itself. Like Ruby is written in C these days still. JavaScript is written in C++, so that's not always the case. And it does not have to be a language written in itself to be real, but eventually, like, either you're writing CPU instructions or you're using another language for this. All right, finally, some last things you might want to look at. Sweet.js. So I told you before, you can't really, like, there's not really good plugin architecture for the Babel parser. Sweet.js is a Mozilla project that basically lets you write macros for JavaScript. So it's basically a compile step that will let you write like custom syntax for JavaScript. So like, let's say you really love Ruby's unless operator, right? Unless identifier, right? And you want to say like, hey, anytime we come against unless, I just want to take this thing and do the not of it. You can actually write that in Sweet.js and have a pre-compile step that will let you write all sorts of like custom code along the way. I don't want to write console log anymore. I want to write print or puts. Cool, you can do it. You can like do very small additions to the language that might be tricky for you to do with Babel parser. This is another parser generator, nearly. One I really want to talk about is, again, James Kyle, who worked on Babel, has this thing called the Babel Handbook, which kind of goes into a lot of this. It's very Babel specific, but it goes into a lot of like how the visitor pattern works in Babel and how to use it along the way. Finally, I mentioned